What else? Okay. So what do you know about light? So one is it's a form of energy. What else?
Isn't light made up of photons?
Okay, very good. It's a form of energy. And then the second thing is that it is made up of those, the energy is in the form of photons. Photons are basically packets of energy. Very good. Photons are packets of energy. What else? Yeah, what else? What do you know about reflection? What is reflection? How do you define reflection? Yes, guys, come on. Reflection is that when a ray of light falls on a surface, then it bounces off. Just touching the surface, it bounces off in the opposite direction, or like it bounces off, and there's a certain angle at which it does that. Okay, so a ray of light comes, falls on the surface, and it bounces off. Like on a surface could be a glass or anything shiny, right? Even water. So this phenomena is called reflection. Now, my other question is, what is refraction? Refraction, R-E-F-R-A-C-T-I-O-N. What is refraction? Refraction. Have you heard of it before? Distortion of light. Very good. Thank you, Kenji. Distortion of light. So reflection simply means that bouncing off of from the surface, bouncing from the surface, you know, just touching the surface and then going off in the other direction. But refraction is actually entering the surface and then getting distorted. Okay, so this is entering, the ray of light enters a medium, and it could be a rare medium, it could be a denser medium, depends. So when the light enters, so light, ray of light enters a medium, and that medium could be rare medium, like for example, air, or it could be denser medium, like for example, a glass, like a light enters a glass, right? So from a rare medium to a denser medium, or from a denser medium to a rarer medium. So whatever this is happening, in that case, the light gets, the ray of lights get distorted. Light gets distorted, D-I-S-T-O-R-T-E-D. Now, what does this mean? So when the ray of light goes, so here's the thing, let's just see that how the behavior of light, we are studying the behavior of light. And it's very interesting. Why are we studying the behavior of light? Because it was a light, the behavior of light, that led us to the discovery of the structure of atom. So if the light is going from, let's put this here, this is the air, and let's say this is the glass. So glass is obviously thicker medium, right? Denser medium. And let's say the ray of light is again air and glass. So when the ray of light goes from air inside the glass, then it bends. That's what distortion is. It bends towards the normal. So it's not the same angle. Here the angle is the same. Whatever angle this side is, whatever the angle on the top one is the same, the angle at the bottom. So this is called a normal, okay? But in this case, the light bends. Light bends, and it bends towards the normal. So this angle is smaller than this angle. So you see that? Next is, if the light is going from the glass, that is from a thicker medium, from a denser medium to a rarer medium, it gets distorted, but it moves away from the normal. So that means that this angle is going to be obviously bigger than this angle. Okay, so it's, in other words, this distortion could be, you know, this just a bending of light away from, or from, or towards the normal. So this is this imaginary line. This is basically an imaginary line that is called the normal. N is normal. So it's just in between line. Okay. So this is one piece we know about light. Besides that, there is also other things. How does the light travel? How does light travel? Yes. You can communicate through chat, guys. Come on. How does light travel? Light travels in a straight line. Okay. So you see it like, they always light travels in a straight line. So when it's traveling straight, yes, these packets of energies are moving like, if there is you've seen it, whenever you have in a room, let's say a window, okay, and in this window, there is a small slit in the window, a little small hole in the window, okay, or in a door. So this is the small hole, and the light from outside is going to come, and it of course, it spreads, but then it travels like straight. It's a straight line, a straight path. Okay. Next is if the light, let's say if you have a bulb or if you have a sunlight here somewhere. So if you have a small slit, even then you will see the light passes through this hole and goes straight. So these are some experiments they do in the physics class in English, in physics class about light. Okay, next thing, if you take a bulb or even the sunlight, let's say this is a sun, or even with a bulb, it will work. Okay, so this light is made to pass through. Now because there's too much light, sometimes you just want to work with a little bit of the light. Okay, so there's a small bit of light coming here, and you keep a prism. A prism, I don't know if you guys seen it, but it's like a pyramid, which is made up of glass. So this is a pyramid, okay? And this pyramid is like a glass, piece. So when the light comes from the sun or from a light source, and the sun passes through this hole, the sunlight passes through the hole, this small slit falls on the side of the prism. This is prism, P-R-I-S-M, prism. So what happens? This light breaks up into 7 colors. And this is violet, indigo, blue, green, yellow, orange, and red. Okay, so this is Vibgyor. So these 7 colors of the light, they are actually, when they mix together, they make the white light. Okay, the white light as we see, the sunlight. Okay, so this is the white light is actually made up of these 7 colors. But these 7 colors only get split, when they strike a certain surface. Same thing you see, it's the rainbow also, same thing. Light from the sun comes and falls on the water molecules, the edge of the water molecules. And that right there, it just splits up into these 7 colors. So that's one piece. Now, this white light that we see is called the visible light. Visible light. And it is in a range. This visible light, it has a range. This white light we see. And do you guys know what that range is? Anyone knows what the range of the white light is, from what nanometers to what nanometers? It's also called a visible, the visible light. Anybody knows? 750 nanometers. And we will talk about what this nanometers means, to 400 nanometers. Okay, that is a range of the white light. Okay, and so this is also, this is a very, very little, like a little range, but then also this is a part of a very big electromagnetic spectrum. So they had discovered actually in the past all these discoveries were happening when they were also discovered radioactivity, when they discovered X-rays, when they discovered gamma radiations, all these things they discovered, and then they found that all these things have energy. And so let's put them in the electromagnetic spectrum, that range on which they are found at. Okay, so here is the electromagnetic spectrum, which ranges from 10 to the power 4 meters, and that meters is the wavelength. And we will discuss this wavelength in a minute, but just for now, hold it. That wavelength is 10 to the power 4. That means 10,000 meters, and all the way till 10 to the power -12 meters. And again, that's the wavelength. So that's the range of the electromagnetic spectrum, wavelength. Okay. And everything else falls in between. What we talked about, the infrared radiations, the microwaves, the radio waves. So we will look into that. But somewhere here is the visible light. Our visible light, our spectrum, which we are used to. This visible light, the range is, the range of this spectrum is from 4 into 10 to the power -7 meters, okay, to 7 into 10 to the power -7 meters. Okay, so that is the range for the visible light. In that range, we see those 7 colors. Okay, now let's just look at a little bit here. 10 to the power 12. Which one is this? These are the gamma radiations, the most, like the dangerous ones, the very high energy radiations. These can kill people. And then we have these radiations, the radio waves. Radio waves are like, radio waves. We listen to radios where nobody gets harmed or hurt by the radio waves. So, but radio waves have very long wavelength. Gamma radiations have very small wavelength. So if you see 10 to the power -12, so that means it's a small number. But 10 to the power 4 positive, that means it's a very big number. So the wavelength of the radio waves is very big. Next, if you look at after the wave, somewhere here comes the microwaves. Microwaves, which we use in the homes to cook food. And, that doesn't harm anybody unless you cook the food too much, then yeah, the food goes bad. After that comes the infrared radiations, IR rays. So IR rays, as you guys know, are used in the medical field, right? To I think in the X-rays, not on the X-rays, sorry, for cancer treatments. So they're using IR. Okay, infrared radiations. After that, UV can kill. Now, here's where things start getting complicated, where UV rays can kill germs, bacteria, viruses, and then comes the X-rays. X-rays can penetrate your body, and they cannot pass through the bones, but X-rays are used, for medical purposes. But once the wavelength begins to decrease, then these radiations start becoming like more and more strong, when they can affect the human beings like bodies, you can say that. But the IR, microwave, radio waves, they are fine. So now, if you look at the visible light now, this means now all of these radiations, first of all, whether it's the gamma rays, X-rays, UV rays, IR rays, microwaves, radio waves, all these travel as waves. Okay, all of them travel as waves. So now we are going to study this, the behavior or the structure of waves. What do we know about waves? Okay, first of all, we know that these especially for all these radiations, all you see this is the electromagnetic spectrum, EMR. So EMR, all of them travel as waves. And whenever we talk about waves, that means we are talking about wavelength, and we are talking about frequency. These are the main things associated with waves. So frequency, QUENCY. Okay. My wavelength you show as lambda, Lambda. It's a Greek letter. And then frequency is nu. So that's the symbol for frequency, and it is called NEW, like nu. Okay. So whenever let's try to understand first of all that waves. So we all know that waves go like this, right? So all of these electromagnetic radiations, let me write this down, electromagnetic radiations, all of them, even the X-rays, they all travel by in this format, the wave-like format. Okay, now let's understand what do you mean by what does a frequency look like and what does a wavelength look like. So here's the wavelength, the distance between one crest and one trough, and frequency is how fast are these waves coming, like that. So how fast, how many times are these going, you see? So this would be long frequency. So first of all, let's look at this is an imaginary line. All of this is imaginary line. And in this imaginary line, the part that is on top, this part that is on top is called crest, C-R-E-S-T. Okay, this is crest, C-R-E-S-T. Okay, and crest, one second. Yeah, crest is on the top. Trough, this is trough. The bottom part is called trough. So, and this is also, the bottom part is trough. Okay, now the distance between two crests or the distance between two troughs is called the wavelength. So this distance is one wavelength, or this distance is one wavelength. So let me write this down. Wavelength is equal to the distance between a crest, one crest, and another, between a crest, one crest, yeah, distance between a crest and a trough. Distance between, like two crests, I would say, between two crests, or two troughs. So that is called the wavelength. Okay, so that's one piece. Next is frequency. Frequency is how many waves are passing, or these are basically the cycles in 1 second. So if you look at it, if you were to count, like in 1 second, how many waves? So see, you see in 1 second, so many waves are going. And if you were to look at this piece and this piece, only one wave is going in 1 second. You see that? So the more the waves are passing, that means more like energy is going. So frequency, let's look at this thing now. Frequency is equal to it's basically cycles per second. So the number of cycles. So cycles per second. Okay, so the frequency, the units for the frequency, the units, or let me write this down also here, that the number of waves passing in 1 second. Okay, so that's what it is. So that's why I call it cycles per second. Okay, then what is the unit for wavelength and what is the unit for frequency? So the wavelength unit is, that is why we said either it is in meters. So METERS. So that's, ideally it is M alone, but I just want to put it as MTS, or so these are all the same. Okay. Another unit is angstrom, ANGSTROM, angstrom. So it's degree A. Okay, so angstrom or meters. So they are interchangeable. And I think there is a conversion factor, which we will look into it when we talk about all these conversions. But the unit for the frequency is hertz. Hertz, H-E-R-T-Z, which we show as Hz. And this also is seconds inverse. So this piece right here, this is called second inverse. And the second inverse also means per second. So either way you could write, okay? So now the number of waves that pass, as we said, in 1 second, that means more energy is passing. All these photons, these and light, we talked about light, we talked about that they are photons. Photons are packets of energy. So many packets of energy, when we talk about these waves, this is how the protons travel. These photons, the photons travel in, so let me write this here, photons travel in waves. And there are two things to the waves, wavelength and frequency. That's the main thing. Okay, now there are other parts to the waves also. One is, this is the wave, this is one part. Second part is frequency. Now let's look at the third part, C part, and that is amplitude. What do you mean by amplitude? So amplitude is amplitude, A-M-P-L-I-T-U-D-E. Okay, now amplitude relates to brightness. So some of the light is very bright, right? It hurts your eyes and you can't like open your eyes and you can't have, and some of the lights are very dim, right? So all this is amplitude, is how bright the light is. So when the brightness, what do you think the brightness of the light is associated with? Yeah, just imagine. What could the brightness of light be associated with? Yes. Any ideas? Okay, one is the frequency. Okay, good, Paulette. Thank you. Any guess? Any guess? Yes. Okay, that guess was with the length of a wave. Okay, good. What else? Yeah, what else do you think? Okay, so this is one wave I drew here. So one is one wave, and then the other one is this one. See that? And then let's do another one. Let's put another one like this one. Okay, so you see these are the three waves, and all three waves. So you see the distance from this line, this is an imaginary line. This part is just an imaginary line. And in this imaginary line, how far the wave travels from here. Okay, how far it is going. All right, now we will see. You see this line from here to here is very small, right? This line from here to here is again very small, but this line from here to this point here and the purple one is very big, but the pink one is the biggest. You see that? The highest is the pink one. So which one is, what do you think, which of these would be the most brightest? The pink, purple, or the green? Just a guess. The height of the wave, very good. So which one do you think? So you already have a clue here. Height of the wave determines the brightness. Very good. So height of the wave determines the brightness. How far away it is from the normal. That means the brighter the light is, the more photons of energy it's carrying, right? the more, so brightness means it's carrying a lot of, photons. And so when it's carrying all these photons, it needs more space. So that is why we see that the brightest is going to be the pink. Brightest is the pink wave, and the dullest is the green one. So less or dimmest, you can say dimmest. I don't know if dimmest is even a word, but anyways, but you get an idea that this is the least bright. And so because it is farther away from that distance, so that means this piece is the amplitude. This piece is the amplitude, how farther away the light is from this imaginary line or normal amplitude. Okay. All right. So the smaller the amplitude, so in other words, the amplitude and the brightness are directly related. So there is a direct relationship between them, that the brightness is directly related to amplitude. The bigger the distance, the more bright the light is. Okay. And the shorter the distance, the less bright the light is going to be. Okay, next is, let's look at another piece, which is, and this also means the number, and the brightness relates to the number of photons. So, obviously it's more photons are needed. Now, another relationship that we have not covered here, which I'm going to just finalize it now, the relationship between frequency and wavelength. Relationship between frequency and wavelength. Frequency and wavelength. Okay. Now, they are inversely related. As you can see, that the longer the wavelength, the longer, see, look at this here, this guy, it's taking very long, very long. So in 1 second, only just one wave is passing. Whereas in this case, lots of waves are passing in 1 second. So that's one thing. So the length of the waves, the length of the wave and the frequency are like inversely related. So we see that the wavelength is inversely proportional to frequency. When the wavelength goes higher, the frequency goes down. And when the wavelength goes down, the frequency goes up. Okay, so wavelength is equal to delta, this lambda, and then frequency is nu. So inverse relationship. Okay, now next thing is, now what do you know in general about, so this gives us some clue about energy, right? What do you know about energy in general? What do you know about energy? All this is interrelated. So what do you know about energy? Yeah, very good, Kenji. Thank you. So energy, what do you guys know? How do you define energy? Come on, guys, you know this one. You guys know here in the class? Anna, do you know anything about, what do you know about energy in general? What do you, just in general, what do you, when you say something has an energy, what does it mean? No idea. Okay, no worries. Okay, what about you guys, rest of the people in the class? Properties, it usually does not share properties with the particles. Okay, yes, it cannot be created or be destroyed. Very good. Thank you, Paulette. It cannot be created. It cannot be destroyed. Yeah, that's the first law of thermodynamics. What else? Okay, a little bit more exact. Kinetic energy. What is kinetic energy? Yeah, kinetic energy. We covered that in thermodynamics. the thermochemistry chapter. Yeah. Come on, guys. What is kinetic energy? What is kinetic energy? Energy from motion. Very good. Thank you, Shaida. Excellent. Very good. See, I like it when, the students think and they participate in the class. It's very, very rich experience for everybody, I think. So very good. Excellent. So kinetic energy is equal to half mv square. So here, when we talk about energy in general, any kind of energy is energy due to motion. So energy, anytime there's going to be energy, I mean, potential energy is by virtue of things remain at rest, but energy in general is motion. So all this we covered last time when we discussed the thermochemistry, right? So energy due to motion is the kinetic energy, but in general, all energy have some relationship to motion. So motion means movement. Okay. Now, when we are talking about movement, when we talk about the waves, obviously waves are not sitting still. The waves are also moving, right? Waves move. And yes, the movement of the waves then gets associated just by virtue of the nature of the waves. The waves move, and that movement gets related to the energy. Just the movement of the waves, the motion of the waves, by just a general fact that if it is a wave, it is going to move, whether it's the ocean, waves on the oceans, water waves, or it's the air, those wind currents, those things. So the wave associated with movement, and that movement, that means the waves are associated with energy. So the common thing that's binding the waves and the energy is the motion. Okay, movement. So waves move, and that movement relates to energy. So that means waves have energy. And if waves have energy, we already know that the waves have wavelength and the waves have a frequency. That means energy also has to have wavelength and energy, wavelength and frequency. Okay, so that means energy, somehow we will have to bring this, because of this relationship with the waves and the motion, the energy should also have somewhere wavelength and frequency. So how do we show this? How do we show this in this relationships, So all that is like, again, beyond the course of this book, but there are certain relationships which we will look at, which actually came from the from experiments and done in physics, and just in general, a lot of things. So just write down this formula, that the relationship, first of all, when we talk about energy, that means we are talking about speed. So here is the speed. This velocity shows that motion. Okay, and this motion relates to speed, the speed with which the photons are moving, the speed of photons, and that speed of photons determines the speed of which of these waves are we talking about, these rays are we talking about, the speed of the gamma radiations, the speed of X-rays, the speed of the UV rays, the speed of IR rays, the speed of microwaves, speed of radio waves, and the speed of our own visible light. And that speed of the own visible light is already known, and that speed is the energy. Let me write this down. Energy associated with the motion, and that motion relates to speed, and that speed is the speed with which the waves move. Speed with which the waves move. Okay. All right. And so for the visible light, there is a speed. And that is, do you guys know that? Visible light. Some of the students are taking physics already. So visible light. So this you must have, read this. Visible light, the speed of the visible light, very common number. The speed of the visible light is the light, our own light is shown as C, and this C is equal to 2.99 into 10 to the power of 8 meters per second. Okay, so that's the speed of our light. And so now they have, through all these experiments and formulas and derivations and math and all that is involved. So the relationship that's good with the speed of light and the frequency and the wavelength is this. Say frequency, and this is nu. So the speed of light or the speed of any waves is equal to the wavelength times the frequency. Wavelength times the frequency. So if you know the speed of light and you know the wavelength, then you can find the frequency. In other words, if you know the two entities, you can find the third one. So the speed of light. Okay, so this is a very important formula. Okay, let's do this thing here. We have one example here, and here, calculate the frequency. Calculate the frequency. Okay, frequency of red light. And that's the of our own visible spectrum. Red light of the wavelength is given to you, which is 6.50 into 10 to the power of 2 nanometers. So again, the wavelength can be measured in angstroms, wavelength can be measured in meters, and I'm going to put a note here that the wavelength can also be put here in the nanometers. NM means nanometers. So like, really small, obviously. We can't see them, so that's why. So here's the example. Calculate the frequency of the red light of wavelength, which is 6.50 into 10 to the power 2 nanometers. Now, the 1 nanometer is, so this is given, or you should make a note of it, given 1 nanometer is equal to 10 to the power 9. 1 meter is 10 to the power 9. 1 meter is 10 to the power 9 nanometers. 10 to the power 9 nanometers. Okay. So this is given, that's the relationship. So obviously this nanometer has to be converted to meters, because we know now something that we already know or will be given to you is the speed of light, which is 2.99 into 10 to the power 8 meters per second. So here you will have to convert this nanometer, nanometer, convert to meters. Okay, because we have to bring it in the formula, and the formula we are going to use is C is equal to wavelength times the frequency. So that's the formula. So all of you guys, I was noting down your test, answers, and I'm noticing it, especially in the lab reports. What you guys are doing is you're just writing the numbers, you're just showing the calculations, which neither you're putting the units, so nor the names, nor the symbols. Just make sure you do that, because that's important. Okay. So anyways, convert to meters. All right. So how would you do that? First of all, so 6.50 into 10 to the power 2 nanometer times, now we need to convert it into meters. 1 meter is equal to 10 to the power 9 nanometer. Okay, so basically when you solve this, this becomes 6.50 into 10 to the power 2 times 10 to the power minus 9 meters, because these are going to cancel out. This nanometer and this nanometer cancels out. So you get 6.50 into 10 to the power minus 7 meters. Okay. All right, so that's the one conversion. Now we have the same units, and now you just have to plug those in. So C is equal to wavelength times the frequency. So we know we need to calculate the frequency, and we have the wavelength. So what will you do? So C divided by the wavelength is equal to the frequency. We need to find the frequency. So C is 2.99 into 10 to the power 8 meters per second divided by the wavelength, which is 6.50 into 10 to the power negative 7 meters. So you see that now meters and meters cancel out. Meter unit and meter cancel out, and you are only left with the unit of per second, and that is the unit of frequency. This is the frequency unit per second. Okay, and this can also be said as, like I said, seconds inverse. But anyways, you do the math. What do you get? 2.99 divided by 6.50. And then, so this comes out to be 2.99 divided by 6.50. Guys, do it.
It's 4.6 times 10 to the 14.
4.6 times 10 to the power 14.
14.
Yeah, so this basically 8 into 10 to the power and then 7. And then when you just do the, is it 4 points? Yeah, 4.6 would be, just 1 second. Do it this way, 2.99 into 2.99. Yeah, I just wanted to, I mean, if you're using the scientific calculator, then yeah, then you would get it. But just keep this in mind that this thing would come out to be 15, 10 to the power 15. And then when you do this, the actual answer then becomes 4.61 into 10 to the power 14. And that is seconds inverse. And remember that seconds inverse also means hertz. So these are the hertz, and the second inverse is equal to 1 hertz. So this also means if the question is asking you, tell it what is the unit in hertz. So it's 4.61 10 to the power 14 hertz, HZ, sorry. All right. Okay, so this is one formula that and the concept regarding that. So kind of we came to know, okay, the relationship that the energy has with the wavelength and the frequencies. Now, they were also studying the, like Bohr had come up with his concept of, Bohr had come up with his structure of atom. And structure of atom for him was just hydrogen. Structure of atom was just hydrogen. He just used hydrogen. And fine, he said that in the center there is a nucleus, and then they were also conducting, all these research for whether there is a gold foil experiment, all that. So yeah, this nucleus contains neutrons, and these neutrons are neutral, and inside there are also protons. These protons are positively charged, and these protons have a mass of 1.00, what is that? I think it's 5 or I don't remember now, 1 point. Let's see. 1.00, I think it is 5 AMU. I'm going to just put it here, 5 AMU. And the other one is 1.006 AMU. So a little bit heavier. And these neutrons basically buffer, because remember, protons and protons are going to repel because they're positively charged. So neutrons help with that buffer. And he said that all around the nucleus is the energy levels where we find the electrons which are negatively charged. And this model was good only for the hydrogen atom, but this does not work for the for like other atoms. So here is this electrons, and electrons, as we said, are the negatively charged, negative charge, and their mass is 1 by 1/836 the size of protons. Okay, and they are found in the energy levels. Okay, but how did we come to know that they are actually present in these energy levels? How do we even know that we can't see that's it's such an interesting chapter. We can't see atoms, and we're talking about all these things. I mean, fine, we have done these experiments to verify, but still, you know, and so here comes Einstein's photoelectric effect, which showed that yes, there is electrons are there, protons are there, neutrons are there, and the electrons are present in the energy level. And what are these electrons doing here? Fine, you know how all this has come. So let's look at the photoelectric effect. And what does photoelectric effect cover? And Einstein actually is famous for theory of relativity. Okay, theory of relativity. Okay, but that's just he's popular for that. E is equal to mc square. E is equal to mc square. He's known for that. But his the Nobel Prize he got was for photoelectric effect, because that led us to the real insights into the structure of atom and so many other things. So here's the thing with the Bohr, like I said, he only studied the hydrogen atom. And so on the hydrogen atoms, all this makes sense, but we will look at more. Okay, so Einstein's got a Nobel Prize, as we said, Einstein, Einstein. Okay, Einstein got his Nobel Prize for this photoelectric. So what is that? Okay, here's the thing. Very interesting. Okay, you take a surface of metal. Okay, a very thin sheet of metal, very thin sheet of metal. Because remember, metals can be made into thin sheets, very malleable. So this is the surface of a metal. And in this case, you know, you can take any metals, and so it will still work. Okay, now what he did was, on the surface of the metal, remember that light moves in straight line, but the visible light moves in straight line, but it moves in the waves. It's a straight line, yes, but it's a wave-like movement. So this is the straight line, but packets of energy, but wave-like. Okay, now here we see the light falls on the surface of the metal. So here is this light passing, falling on the surface of the metal. Okay. Okay. The light keeps falling on the surface of the metal, and yeah, a light is, 1 second. Yeah, so light, remember light is h nu. We show light as h nu. So this is light as h nu. That means that a light of certain frequency, light of certain frequency, when that strikes on the surface of the metal, very interesting is that the electrons are emitted. And this only happens at a certain threshold frequency. So when you put the light, strike the light, and ordinary light is passing, nothing is happening. We don't see from the aluminum foils electrons coming up. But if you strike the light of a certain frequency, this is the formula for the light. This is how you show h nu. H is Planck's constant, when we will study that in a minute. But that light is associated with frequency. So when this frequency, in other words, how fast are these guys, how fast are these waves coming? That's what it means. Frequency is that. So when the light of certain frequency strikes, then the electrons are emitted. Okay, it doesn't strike, it doesn't happen if it's below that threshold, only at that certain threshold. Now, he used it on all the kinds of metals, and it's not that the same kind of frequency worked on all the metals. No, for every single metal, a certain frequency only worked. That's a very important part. You see that? So this frequency is called a threshold frequency, and that threshold frequency is very unique to every metal. And remember, everything is made up of atoms in the end. So where are these electrons coming? As Bohr said, oh, these electrons are coming from the atom, from the outside of the atom, the outside the nucleus, right? And so these electrons can leave the atom. That was a very interesting thing. And this only occurs when there is a certain light of certain frequency. Below this frequency, the electrons are not emitted. Higher, nothing happens. But that's one piece. Second piece is also how many electrons are emitted. So the number of electrons emitted, that depends. So the number of electrons increased when the intensity of the light increased. Intensity of the light increased. Okay, so that means the more the photons, the more intense the light, that certain frequency of that light was, the more the electrons were emitted. And second thing was that the kinetic energy of photons, of these electrons, sorry. Okay, that kinetic energy of the electrons also increased when the frequency, the threshold frequency, like at that threshold frequency that happened. So the threshold frequency of the light, like in other words, when you increase how much light at that certain frequency you are putting, so the total number of electrons and the kinetic energy of the electrons also increased. So so this means that the intensity of light and frequency of light are, so here, let me write this down here. Intensity of light and frequency of light are mutually exclusive. Frequency of light are the more the intensity. Yeah, but okay, don't write that. So because it's only occurring at a certain threshold frequency, not above or below. So leave that. Okay. Yeah, so the only thing here we can say is that the number of, so this also has to, the intensity of light relates to the photons. The more photons strike, the more electrons are going to be emitted. That's what it means. Okay. So this gave us some insights that every species, every atom, atom that belongs to a certain, certain element has something to do with the frequency of the light and you know, why a certain frequency of light only would emit the electrons? Why not above and below? So that has to do something with where are the electrons placed, or the energy of the electrons, or the nuclear pull of the in the atom, or something is going on. But that was a very powerful, you know, observation that came out from this photoelectric effect experiment. Next is the black body radiations. It's a very interesting experiment which was conducted by Planck, and this is called the Incandescent Experiment. So Incandescent, DESCENCE, Incandescence Experiment, and this was conducted by Planck, PLANCK, okay, Max Planck. And this commonly is also called black body radiations. Black body radiations. Okay, now, so this is like this whole chapter is such an interesting, like it's a history, it's a story also, like how did we come to know the structure of atom? So you see, so much is gone just to get to the structure of atom, something that we don't even see, we could not see at that time. Now, of course, we have ways of looking at the atoms also. Anyway, so here is this. What does this mean? Okay. Dark room, pitch dark room. Don't bring any light from outside, like absolutely dark room. In that dark room is the oven, a very specially made oven in which no light is going to be involved anywhere. Okay, so oven. In that oven, they put the metals, you know, which we know that they contain only one type of particles. So metals, which are only made up of, you know, single particles, and the single particles, obviously they're trying to study the structure of atoms. So, so single atoms, I'm going to write down here. So pure, like absolutely pure substances. So here is this pure metals. And these metals, obviously, you know, they were getting from metallurgy, they bring rocks, they start hitting them, they start heating these rocks, and then they start cracking, and then that's how they get the pure metals. Anyways, no light is coming from outside. No light from outside. Okay, so how difficult this must have been. The reason why he was trying to do that, he said, okay, we understand you strike light on a surface of a metal and it begins to emit electrons. So that means, you know, the electrons are present there. It is there, undoubtedly. And Bohr, he came up with, basically, this is the atomic theory. This is just a theory. He was unable to, like, you know, say, but Bohr said that, okay, this is, Dalton said that all substances are made up of atoms, and Bohr said, yeah, this could be the structure of atoms. So this is just a theoretical piece. And then, you know, we understood the behavior of the light. So here, interesting part here is that we understand that is what they were trying to discover at that time was that is there a relationship between light and matter. So they were trying to study this relationship between light and matter. I mean, fine, you know, Einstein is like father, of course, of science, and everybody believed him, but that doesn't mean that when you have scientific experiments, you're not going to critique. Yeah, Kenji, I'm going to put those videos. Yeah, but thank you so much. This is good. Thank you. So he was saying that, so we understood the behavior of light. Now here, what I was saying is that fine, the electrons are being emitted from the surface of the atom, from the surface of these elements. Are you sure that they're coming from the surface of the metal? What maybe they're coming from the light? So we want, like, there's always this speculation and critiquing and always trying to figure out that is this there's a lot of debating going on. So it's all healthy, right? It's nothing wrong with the, questioning things, because that's an inquiry. That's all science is all about. So that's incandescence experiment conducted by Planck was to study that. Fine, we understand that light comes and falls on the matter. But can the matter emit light? Right? So is there a relationship between light and matters? So can the can a matter emit light? Can a matter emit light? Okay. So this is what, he wanted to figure that out. So, and that's what led to the discovery, not just a discovery, the understanding of these energy levels. Without this incandescent experiment, we would have not done anything. So this energy levels, as you see, these are quantized. These energy levels quantized. Quantized means how much is that energy? How much is the energy in these energy level? So this is what, that understanding came from here. So he put them in a box, in an oven, all these one rock at a time, obviously, and raised the temperature, continues to increase the temperature, several thousands degrees Celsius, several thousands degrees Celsius. Okay. And inside is the rock. And it's pitch dark, no light from outside. After some time, he begins to see that a light is coming out from the oven or from the matter. So light was being emitted from the metals or the rocks, or light emitted from the metals. Okay. That means that the matter is capable of giving away light or giving light, right? So we were trying to figure out, where is this light coming from then? Where is the light coming from? What do you guys think? And then besides that, at every temperature, there was a color of light, like, for example, and also with the nature of the metal, like, for example, if it was a potassium, the maximum light, it gave like the other lights also, like the majority of the light is the violet color for potassium. Okay, and then for sodium and A, so I'm not going to just put there the symbols. So for potassium, the majority of the color was violet. Sodium, the majority of the color was orange. Okay, and then for lithium, the majority color for a long time was red color. Then strontium, the majority color was crimson, dark, red, beautiful crimson color. And then crimson, and then barium gave green color. Barium gave green color. Okay, and then calcium, when calcium was kept there, it gave yellowish red color. Yellow, but mostly like with red tinge to it. So yellow, red, mixed color. And then lead, when lead was heated, lead gives grayish white color. You see, so on top of that, all these different colors of light. So what does this mean? So previous view was that the matter and the light are like exclusive, like are distinct, are separate from each other. But this proved that matter and light are a part of each other. Matter and light are connected, are together. Okay. These also proved that matter could absorb and emit any amount of energy. So some of this energy is, so that means that the matter is capable, there is some energy present inside the matter. And this energy, their energy is associated with light. We know what the white light is. White light is all these colors, Vibgyor, right? So energy is associated with light. And so that means that the matter has that, like what the matter is made up of atoms, and atoms are associated with some form of energy. There is some energy present inside the atoms, and this energy is associated with colors. And what do these colors signify? Or where do they come from? There is the wavelength and the frequency is associated with the colors of light. Okay, so we see that he obviously understood the relationship that energy is equal to mass into the speed of light. So energy is equal to mass. This is Einstein's E is equal to mc square. And then through more derivations, he came up with a constant. He continuously repeated all these experiments, with different amounts, different amount of temperature. So it's like becomes a lifelong activity for these people, right? So H is equal to 6. The value he came up with is a constant, 6.6 into 6.626. 6.626 into 10 to the power negative 34 joules times second. And all this is through derivation, so don't worry about that. So we know that the change in energy is equal to h nu, and h is that Planck's constant, nu is that frequency. Okay, and this shows that the energy is quantized. In other words, the colors of the light are associated with energy. Okay, the colors of the light are associated with that. Energy could be gained or lost in the whole number multiples of. So I'll just show you another piece right here, which is the quantum mechanical model of atom. Quantum mechanical model of atom. Quantum. So all this is quantum, like at the quantum level, quantum mechanical model of atom. So basically we are trying to now figure out that, okay, what is the value of that energy that is present inside the atoms? Fine, we understand these atoms have energy levels, and we can figure out now based on the colors of the light alone from Planck's experiment that what is the value of that energy. So there's a few things we know about the atoms. So this is what, from this led us to understand what must be happening. One is the nucleus, that's fine. Outside the nucleus is the energy level. So this is energy level 1, energy level 2, energy level 3, energy level 4, okay. Now, remember that the electrons in the energy levels, so energy level 1, 2, 3, and 4, and the electrons can jump from a lower energy level to a higher energy level, from E1 to E2, or from E1 to E3, or from E1 to E4, or from which one we did do, or from E2 to E4, or from E2 to E3, all these. So jumping from lower energy to a higher energy level. And whenever the electron does that, it emits radiations. So electrons jumping from lower energy level to higher energy level. And whenever the electron does that, it emits light. And this light is of a certain color. light of certain color, and that color is associated with wavelength and frequency. Okay, so this is certain color, and the color of light relates to energy is equal to, remember, no, see the speed of, so that was the speed of light. The color of the light is related to the wavelength and frequency. Okay. And that wavelength and frequency, as far as that wavelength and frequency is there is energy, and that's change in energy, change in energy. So with that, we will said we were 100% sure that E2 is, that E1 is a lower energy state, E2 is a higher energy state, E3 is the higher, and then E4, the further away you go from the nucleus, the value of the energy is also increasing. So you see, each one of these, they emit a certain color of light, and that color of light is this is light. H nu is light. Okay, that color of light is associated with, as we talked about, energy. And that energy, we were able to tell 100% what is the value of that energy. And depending upon the nature of the atom, which atom it was, the size of these energy levels is also going to change. This is going to be like small atoms, small energy levels, small like the size, the radial size. The big energy levels will be, again, the bigger the atoms, the bigger the energy, the more spread out. And based on that, the electrons, when they jump, the colors are also going to change. Okay, so that is the emission spectrum. This is emission spectrum. Emission, EMISSION. I don't know if it's double M or not. Emission spectra, this is called. Okay, and emission spectra, we'll show you in a minute, but there's something else also happens. It's not just one way, it's the other way also. And that other way is that there is absorption spectrum also. And the absorption spectrum is when the electron jumps from a higher energy level to a lower energy level. One second, excited energy. Yeah, from lower to higher is the absorption. Sorry, this is the absorption spectra, not the emission. This one is the absorption, ABSORPTION, absorption. So lower to higher, lower to higher. When the jumping is, then it's absorbing. But when it's jumping from higher to lower, then it's emission. Yeah, sorry about that. So just fix it if you guys got it. So moving from E4 to E1, E3 to E1, E2 to E1, or even moving from E4 to E3 or E3 to E2, all these are like, so this is the, this is also, they are going to, light is going to be involved even when it is, this is the emission spectra, EMISSION, emission spectra. So emission spectra, remember, anytime we talk about spectra, that means it is associated. Spectra is associated with colors, and those colors are associated with energy. And we were able to get to the value of this energy. Okay, so what are the formulas for that? Okay, the formula is delta E is equal to H nu, that's the H is the Planck's constant, and C nu is the frequency. And remember that C is equal to lambda times nu, that is a wavelength times frequency. So you can move things around. You can put C over frequency, C over wavelength is equal to frequency. So H, Planck's constant, times C is the speed of light divided by the wavelength. So these are the relationships. So when the electrons are jumping from whatever energy level they are, you can actually calculate. So here's, let's do this again. So this is one energy level. This is the second energy level. This is the third energy level. This is the fourth energy level. So E, so leave this. So here is the electron jumping from this to here, or electron jumping from here to here, or from here to here. Okay, so how many did I make? 1, 2, 3, 4. I need to make one more, and then one more here, and that is, yeah. Okay, so this would be energy level 1, energy 1, energy 2, energy 3, and energy 4. And what are their values then? The values are every time HC over, HC over the wavelength, HC over lambda 3, it's not H, wait a minute, just a minute. H C over lambda 4, H C over lambda 3, H C over lambda 2, H C over lambda 1. Okay, so wavelength 1, 2, 3, 4. And here I have just shown you like they are the same distance, but obviously, you know, they are different colors. So the different distances are also different from the, like, vary from the nucleus. So these colors are, you know, this explains the different colors. So the colors are due to basically the wavelength of light. Okay, all right, let's say now there are two types of spectrum. Spectrum are like, you know, like the fingerprint of the metals. So it's called spectra. Okay, what is happening here? My iPad might die. Okay, so just give me 1 minute. Okay, so spectra. Okay, so spectra, when we talk about spectra, there are two types. One is the just like a continuous spectra, continuous, like the ones that you see in rainbow. Okay, continuous spectra, and that is, you can very clearly see the, like a bands, right? So continuous spectra is all colors, you know, they have a certain like a depth or a spread. So it's more like a spread out spread, and or you can say like these are the bands of light, bands of light. Okay, so like rainbow. And next is the line spectra. Now that is a fingerprint. That is what led us to 100% be confirmed about. One is the structure of atom, the energy levels, how many electrons there are, how many protons there are, those things. Okay, so the next is the line spectrum. So anytime you see that, anytime a meteor or you know, some outer object strikes the earth, right? Anytime a meteor, something strikes the earth and we have a new element or something new shows up on the earth, which we don't know, you know, we have never seen it. The only way to determine what it is through the line spectra. Line spectrum, as it says, line. So these are very discrete lines, And these are the fingerprints of the elements. There are 118 elements present on the Earth. Not a single one of them will have the same line spectra. So these are very discrete lines. And these discrete lines, they signify, they basically, they are characteristics. So these discrete lines, they are very specific to the elements, okay, of different colors. So let me see if I can show you. I don't know. Where is that? So let me see if I can show. Oh my God, what the hell is that? Sorry about that. That's the thing with these. Okay, I'll look into it and I'll show you, where these, how does it look like? But anyways, here's the thing, just to give you an idea, like you will see these lines, for like some element. I mean, I can, let us say, for example, for gold, you would see like a whole bunch of red lines and then a few of the blue lines, and then maybe one line of a green one, like when the light is passed through them. So, or maybe a purple line somewhere here, 1 or 2 purple lines, something. So this would be a very unique spectra. There could be another spectra of another element which will have lots of yellow lines in one line, and very discrete line. It's not like they are touching each other. No, 1, 2, let's get this color is not coming out. Like, let's say orange color. So lots of orange lines, and then let's say 1 or 2 purple line, like these type, and then nothing else. Like, or there could be one that has only blue lines, nothing else, only blue lines. So this is very, very, very characteristic of substances. So how do they get that? How do you get actually we do a lab, okay? So it's unfortunate that we guys can't have all the labs, but this is what they do. They take these tubes, and these tubes have sealed. These tubes are sealed from both the sides, and inside the tubes are these gases. One gas, let's say gaseous metals. Like gaseous metals would be the like the metals. You take the metals and you heat them at a very, like, say, let's say mercury. You take mercury, you heat it at such a high temperature that it begins to, obviously it's a liquid, then it begins to boil, and then it converts into the gaseous forms, the vapors. So basically vapors of the elements, or the elements in the gaseous state, are found in these tubes. So elements in gaseous state, their gaseous state, all elements, you can convert them to gases just by heating them. So that's the purest form the elements can be found. So elements in the gaseous state, it could be, it could be any of the gases like oxygen, oxygen heated up, or xenon, we do it of xenon, we do mercury, we do for sodium, so sodium gives a very bright yellow light. But anyways, so how are you going to heat it? We heat them after passing the electrical current. So one side is positive and the other is negative, and current is passed through. So current is actually gives you a very high what do you call the a very high temperature. So when the current is passed, what happens? Electrons jump from lower to higher. So we see in colleges we generally do these these absorption spectra. So electrons jump from lower to high energy levels, and when they do that, they emit light. But this is not just any light. The light is basically like in a pattern, in some kind of pattern that is called the spectrum. And then that is used to identify unknown. What is there? Okay, which one is that? So if it's an element that is already known, then you match it. But if it is something new, then obviously you've never seen that spectra before. So that's how we determine whether the things coming from the outer space are, what is the identity of those substances. So it's very interesting. Some of the elements, like Neptunium, like, those types. And I don't know if it's actually Neptunium but some of them did come, from the outer space. So that's how, we identified them. So this is one line spectrum. This is another one. And then this is another one. Okay. Okay. So that's the thing with that. And now let's look at the okay, let's look at this one. The Bohr's model, back to Bohr's model. So yeah, we understood that what Bohr was talking about, that the electrons are in these energy levels, and then we can understand, like, we kind of get an idea of what the values are. So here's this expression of the Bohr's model. This is a formula already. So, we are not doing any derivations in this class. So just know the formulas, that energy is equal to negative 2.178 into 10 to the power negative 18 joules times z square over n square. So what does these mean? All of them. So here, E is obviously the energy levels in the hydrogen atom, energy levels in hydrogen atom, and that is E. Okay. Next, J, obviously, joules, Joules. The energy is measured in joules, so that is the value of J. What is Z square? Z square. What is Z? You guys have read that already. So what is Z? Z stands for. Yeah. Z, what is Z? You already done that. You already know it from your very, very early chemistry classes. Z stands for what? Z. Remember mass number? Very first class we talked about mass number. The majority of the mass of an atom, where is it? Where is the majority of the mass of an atom? Where is it? Where is it located? Yeah, Anna, do you know? Where is the mass of an atom? Majority of the mass of the atom located? Nucleus. Very good. So that mass number is due to the nucleus. So nucleus, what is there inside the nucleus? What is inside the nucleus?
Protons and neutrons.
Protons and neutrons. So if there are protons, so what is the charge on the nucleus? What's the charge on the nucleus? Positive charge. Very good. So this is also called the nuclear charge. So Z square is the nuclear charge. So as many protons are there, that many number of plus charges are going to be there on the nucleus. So nuclear charge. And nuclear charge is the number depending upon the number of protons. Okay, then comes the n square. Now n square is the integer that relates to the radius of the orbit. So integer that relates to the radius. The radius of the orbit means a radius of the, like in the of the atoms. So integer that relates to the radius of, in olden days, they actually called it orbit only, actually. Okay, and that is n square. Okay, n square. Orbit, because Bohr model is based on like the solar system. The sun is in the center and outside are these planets, you know, those type of thing. So that is why he used the word orbit for that. Orbit of the planets, you know, those things. Okay, now, why is there a negative sign? What does a negative sign could mean? Negative energy. So negative sign means that energy of the electron is lower when it is closer to the nucleus. So the closer the electron is to the nucleus, the closer the electron is to the nucleus, the more, you know, it's more attracted to the nucleus. So there's something to do with the nuclear attraction here also. Nuclear attraction is playing a role. The number of protons present inside the nucleus, the size of the nucleus itself is also playing a role in defining the energy levels. And so those things, you know, so anyways, now imagine if the electron is going very far away from the nucleus, then its energy becomes zero, like mathematically. I mean, obviously it doesn't mean that, but zero would be a very big number then. Okay, now look at this, an example here. Let's do this example, this problem. Okay, example is that an electron jumps, okay, down, and it's jumping from a higher to a lower. Electron jumps down from energy level that is 6 to energy level that is 1, okay? Then calculate the delta E, which is what is the change in energy? Change in energy. How much energy is released when the electron jumps from a higher energy, which is the number 6, to a lower energy? Okay, so simple, from N6, first calculate the energy that is present in N6. That is going to be, when N is equal to 6, when N is equal to 6, then the energy, let's call it E6, is equal to the same formula, minus 2.178 into 10 to the power negative 18 joules times, now remember Z square, this is, he was talking about hydrogen. Bohr's model is only about hydrogen and nothing else. So what would be the nuclear charge on hydrogen? What is the nuclear charge on hydrogen? Value of Z square, the mass number of hydrogen, what is that? Come on, guys. For hydrogen, what is the value of the mass? What is the mass number of hydrogen? 1, very good. So the value of H, so that means Z is equal to 1, which is the mass number of hydrogen is equal to 1. So all this Bohr model is only for hydrogen. It's very interesting. All this hard work for just after one atom, and that also the baby of the whole periodic table. Anyways, so here comes the Z square over N square. So Z square is 1 square over N square. N square is 6 square. Okay, which is the N is that integer, that how far it is, the N, that's what it means. Okay, so when you solve this whole thing, it comes out to be negative. Let's just move on further with this. So 6.050 into 10 to the power negative 20 joules. Okay, so this is one piece. Now, when N is equal to 1, then the value of energy E1 is negative 2.178 into 10 to the power negative 18 joules times 1 square for again for hydrogen over 1 square. Okay, that's a value of n, and this comes out to be negative 2.178 into 10 to the power negative 18 joules. Now tell me, which one is closer to the nucleus in general, E1 or E6 in general? I just want to know from you guys.
E1.
E1. So if you look at it, this guy 10 to the power negative 20, this is 10 to the power negative 18. Okay, so the one that is closer to the nucleus is like it will have like this is bigger number. This is in comparison. The top one is so let me just put it here. So E1 is bigger than E6, but only in the terms that because it's closer to the nucleus. So the more negative energy sign, so more negative energy means it's closer to the nucleus. So E1 is closer to the nucleus than the E6. Okay, now what is the value of delta E? Delta E is equal to, now remember, final minus initial. Which one is final? Which one is final? E1 or E6 is final? Which one? Final is E1. Very good. Because it is jumping from the 6th to the first one. So it was here first at E6, then it came to E1. So that is why we will have the final is E1 and initial is E6. This is sometimes students make mistakes here. E1 minus E6. Okay, and so we have here negative 2.178 into 10 to the power negative 18, okay, minus negative 6.050 into 10 to the power negative 20 joules. This is also joules. Okay, so when you do all the subtraction, this gives you negative 2.117 into 10 to the power negative 18 joules. So this is the amount of energy that is lost when the electron jumps from the higher energy to the lower energy. Negative sign, energy released. You know, you studied that in thermodynamics. So in thermochemistry, sorry. So this is the negative sign means energy is released. Okay, so when this is released, where is it going? It's going in the form of colors of light to the surroundings. You see the fireworks and all, that's what it is. The electrons jumping and giving you all those nice colors. That's what it is. Okay, so that was Bohr's model. And so this is the general equation moving forward. You can also, this is another one, general equation for any. So this was from E6 to E1, but it could go from E2 to E3 to E2 and so forth. So what is a general equation? So delta E is equal to E final, whatever the final, value it goes to, minus E initial. Okay, and that is minus 2.178 into 10 to the power negative 18 joules. Okay, times Now, since this is for hydrogen atom only, for hydrogen only, so the value of z square is always going to be 1 square. So why to write z square all the time? It's 1 square over whatever the n is, whatever the final, you get that piece, and then minus 2.178 into 10 to the power negative 18 joules times 1 square over n squared. Sorry, this is square. This is initial. So this is one thing you guys are going to do. And then the second thing is, when all of this is settled, this delta E value further can also be expressed as delta E is equal to negative 2.178 into 10 to the power negative 18 joules times, so this is one piece, times 1 over n square final minus 1 over n square initial. Okay, so these are the two things you are going to, like, you can just keep this formula of copy. See, some of the stuff that I've given you in your handout is from your previous, which you should know ideally, but you will have to make more notes from your side. So just make sure that, you copy these for the exam and so forth, or for your homework and quizzes and those things. Okay, guys? But here's a problem, why we had to do all that, because Bohr model does not work for other atoms, not even for helium. Bohr model fails for other atoms. It holds very true for hydrogen only. So that's the problem with the Bohr model. All this math we did and everything, it just only works for one matter. So it doesn't solve our purpose. That's where Schrödinger came up with his idea of, I said, okay, we understand, okay, at least we understand that there are electrons present in the energy level, and these energy levels can be quantified, but we have to now understand the behavior of the electrons, study the electrons more, what is going on. So that's where the concept of wave mechanics came in. Now that's where, it's such an amazing quantum mechanics, quantum, physics and let me write the spelling down. Quantum chemistry and physics. It's the same thing. Basically, they're trying to understand the structure of atom. Okay, but what did they say? Schrödinger, SCHRODINGR, and de Broglie and Hund. Okay, these people, and there was one, Polly also worked on this, Polly. And then maybe there are a few others, but these guys, they all worked on figuring out, but more work is obviously done by Schrödinger. And he came up with his equation on wave mechanics. What he used here, it's understand the behavior. We know that the light moves in patterns, right? Light moves in these waves. So study the structure of waves. So he used music and musical instrument, which is, guitar, the chords, the musical instruments, the ones with the chords. And like, for example, guitar. Trying to understand waves from there, he got the idea about the structure of waves and all that. So we will study this further next time when you guys come. But right now we need to just close. So, Heisenberg, Hund and Heisenberg also was there. I forgot that one. Heisenberg, Heisenberg. Heisenberg. Okay, so we will study this more about this and what is this, wave equation, how did it come by, those things. So it's very interesting stuff. But right now we need to close. Okay, guys? Okay, any questions you guys have? Anyone has any questions? No, but thank you. Excellent classroom participation. Appreciate it, guys. So very good thoughts. Very good. Thank you, Mikala. Yeah, we will study that cat's experiment. You know, the cat die or cat did not die. We will do this next time when you come. I want to know, what do you guys think about the cat? Okay. All right. Okay. Thank you. Bye. Bye. Take care, guys. Okay. Bye-bye. Bye, everyone.